Well, first of you, thank you very much of organizing this very exciting digital seminar. I mean, if I see the number of participants, actually, it's even better to have it digital than to being on a real conference, where sometimes you find yourself with 6 or 10 people in the audience. So at least this is a possibility to spread some information more widely. And as we are recorded, even people who don't have time, now currently at lunchtime, can listen to this. When I was preparing this talk, I decided to split my talk in 3 sections, which I will explain you later, but it will all be around electrochemical sensors for pathogens. So at the beginning, we will look at bacteria and later at viruses. And when I say advanced nanostructures, I will take it a little bit more widely. So part of the nanostructures will be linked to surface nanostructures, in particular graphene. And then later on, I will look at more biological nanostructures and how we can use them for sensing in these fields. Now, I'm not sure if everybody knows me and our group, and it's always an effort of people together when you work in fields. So I decided the first 2 slides, I will give you a brief overview what we actually do in the lab. Because as you will figure out, environmental sensing is not our main topic. It actually only became some months ago. And I will show you some of our latest results, what we do actually on viral sensing on this. So we are a group of a certain amount of permanent researchers, as it's in France. So you have sort of a parallel structure. But the idea is that we all work together on the topic using chemistry and material science to respond to the unmet medical needs. So it's this medical field is very much put in forefront. So here we work on nanomedicine related issue, how you can inhibit biofilm formation, how you can treat probably one day or later with nanostructures and laser therapies, protein aggregations in your eyes. But we also do a lot of drug delivery, putting it on the skin and using this type of watches to have an on-demand delivery of drugs. The second type of research we do in our field is mostly based on sensing applications. So we have here notably electrochemical, electrical, and plasmonic sensors in the foreground, and this I will talk more lately. And we were sort of lucky that in the last months, we created actually a company around portable biosensors called Cordial ID, where with your mobile phone, you can now, if you want, detect if you are COVID positive or negative. But this we will come toward it later. So the outline of my talk is I will look into a development of an electrochemical sensors for E. coli, and notably will focus on the way we can put reduced graphene oxide on electrodes, but also locally on this. And so if you're more interested, this is linked to a paper we have published 3 years ago. Then I will quickly drift a little bit more to this electrical biosensors on viruses. Even though it's not environmental, it's important because some of the notations actually we are currently using for the last example I want to give you, and this is then on the electrochemical biosensing of grapevine fennel leaf viruses using nanostructures. So let's get started. I mean, I think everybody knows nowadays that infectious diseases are a leading cause of death for humans, animals, but also for plants. And we speak economic burdens for hospitals, for the environment. So one essential element for implanting a rapid and efficient responses for infectious diseases are biosensors. So why biosensors are so different to other diagnostics? So I decided to put up this slide to put us all on the right wavelengths. You know, culture-based methods are beautiful. You can distinguish between the bacteria, but it takes several days until you have a result. The same is for staining. You can stain them, but you need big equipment. So when it comes to diagnostics of bacteria, I would say currently there are mainly 2 platforms available. These are molecular techniques, fingerprint techniques, which are either based on fluorescence in situ hybridization like fish or lump. And this is indirectly related to PCR results, which are very sensitive, but are rather time consuming and actually costly and need large equipment. So you come to the other side now, where you use immunological based detection methods, mostly ELISA based ones, where you have a variety of ELISA techniques, immunomagnetic separation, competitive, two structures, ELISA methods. But what the issue with ELISA often is, there's a limited detection limit, in particular when it comes to bacteria and viruses. And this is where biosensors could not only kick in because of the selectivity and specificity, but ELISA stays a laboratory-based instrument. So you could not imagine as a point of care device, which eventually we want to develop with biosensors. So I work a lot on electrochemical biosensors. What one has to know for a biosensor, if one not is in the field, or a biosensor recognizes a target marker, which will be in this case now a bacteria, and it's characterized by an interaction with the analyte, the bacteria, with a ligand to the surface. So this bioreceptor is extremely crucial component in this biochemical sensing events. And I made you here a list. It's not an exhaustive list of type of receptors you can put on these interfaces. So there can be DNA, antibodies, aptamers, especially when it comes to bacteria. We tried antibacterial peptides as well as carbohydrate or phages. But they are one important part of a biosensors, but then there are two other important parts. That means the type of material you will use in these electrochemical sensors. And it has been shown that if 2D materials, especially like graphene, and if they are deposited in the right way, might extremely enhance electrochemical signals. And I will show you how this can be done. So we have seen interface, we have the ligand, but then the ligand has to be covalently mostly bound or integrated on these chips in a robust and correct way. So there are a variety of surface chemistries available of doing this, and I will guide you through two of them we have been using. So the other thing about electrochemical biosensors is, and this is often very confusing for lots of people, is the variety of readouts you can have. You can have amperometric readout, where you can have a step integration of different concentration of bacteria, and you will see the result. You can do it more indirectly using different pulse photometry, which has the best detection limits of all of these electrochemical methods. But you can also go to more complex readouts like electrochemical impedance spectroscopy, or you can actually change completely from electrochemical to electrical readout, where we can use this transfer characteristics to see actually for sensing applications. So now I said I want to talk about advances in nanomaterials, and notably everything which is around graphene. So the question is, why are we also interested in graphene technologies for sensing? But first, graphene, I believe, is still one of the ideal materials for electrochemical sensors, and I put down some of the advantages here. It's extremely good in electrochemical conductivity. It's bendable. That means it will allow you one day or the other integrated on humans, but eventually also on animals, on plants, so they can carry it with them. It's a rather biocompatible material, so you will have no issues of degrading your analyte by the interface for itself. But then what's most important is you can have a variety of different composition of this material. So there's this classical monolayer graphene material, but we can go back to chemical derived materials like reduced graphene oxide. You can make it porous to increase the surface area of this material. You can dope it if you want higher conductivity. You can put nanomaterials on it. And all this type of different materials will result in a different charge fair characteristic of these interfaces. So simple for the beauty of comparing it, what we played around it, we did these different materials. So gold, we coated monolayer gold, reduced graphene oxide, porous, and nitrogen doped porous, reduced graphene oxide. And we used ferrocene as a classical reduced redox couple. And you see actually from compared to the gold electrode. If you go to the nitrochipped porous graphene oxide electrode, you have a 2 to 3 times higher electron transfer on these materials. And this higher transfer will actually allow you having better sensitivities in the long run if you get the right receptor on these interfaces for sensing. So there are materials here. The question always for electrochemistry is, how are you able to put them on interfaces? There are a variety of ways you can choose. You can either do a CVD transfer, that's wet transfers, you do drop casting, you can do electrostatic interactions, electrochemical reduction. What we like a lot, it's something called electrophoretic deposition. All of you actually know the process of electrophoretic deposition, because I guess most of you have a car, and all the colors on the cars, actually this type of polymers are deposited nowadays in the automobile industry by electrophoretic depositions. So what is electrophoretic deposition? And I will explain it using graphene oxide as an example. So graphene oxide, if you look at its structure for itself, it's a negatively charged nanomaterial. That means if you have 2 plates, an anode and a cathode, and you apply a tension between them, you will have the negatively charged species moving to the anode and the positively charged to the cathode. So graphene oxide will therefore move to the anode. If you now put this an interface into graphene oxide suspension and you apply different potentials, you see actually what's happening. So you have here graphs where you see the current over time for a potential of 1.5 to 3, and then from 4 to 10. I put them in 2 different slides because you see immediately the difference at very low voltages. You see a decrease in current in time, and out of a sudden, at a certain threshold, you start to have an increase of the current over time. Well, an increase in current is always linked to an increase in conductivity, and a decrease in current to an insulating effect. Now, graphene oxide, we know by its nature, it's an insulator, and if it moves to the anode, it definitely cannot be reduced. So if you will have a deposition of graphene oxide on an interface, you should expect actually a decrease in current, which is actually happening up to this threshold of 3 volts. And if you look a little bit at these optical images of an interface of 1.5, you hardly see the film, but of 2.5, you already see a very nice smooth film on it, which is also in agreement with the optical images you see just below. But then actually, if you go to higher voltages, out of a sudden, the current dramatically increases. And people were puzzled over while this increase in current is happening. And it actually can be easily explained that on the top of the electrophoretic deposition process, you will have another electrochemical process actually happening, which forms bubbles. And towards to this bubble formation, you actually rip off the film you just formed. And this you see very nicely actually in this SE images below. And therefore, you have to tune very carefully in this process which potential you want to do. But the beauty of this electrophoretic deposition is now you can deposit it on large electrodes. You can get your electrical charge for enhancement, but if you look at the image completely on the right side of my slide, it allows you actually also local deposition of these materials on interfaces. That means if you work with more complex interdigitated electrodes, you can get this graphene material exactly where you want to do it. So what did we do with this electrophoretic graphene deposits for bacteria sensing? So here I want to add now a second part on it. We have been shown and I think everybody knows that materials like PUE, who have a lot of NH2 groups, are rather toxic for bacteria, but also will increase the adhesion, therefore, from the bacteria to the interface. So what we did in this work, we not opted for an anodic electrophoretic deposition, but we actually opted for a cathodic electrophoretic deposition, which has 2 advantages. If you combine graphene oxide with a polycharged polymer like PUE, you actually get a material which now has a potential, positively potential. That means it will actually move to the cathode. And this will have two effects. So you will have a deposition, but you will also at the same time reduce the graphene oxide to reduce graphene oxide. So you will end up with a matrix which is really covered on your working electrode as you want it, but has a very nice stable film, and you have the great electrochemical properties of reduced graphene oxide visible. So actually, if you look at these SEM images on it, you see that these bacteria can actually stick, but that bacteria can stick specifically, and that we get rid of background current. We had now to use some surface chemistry approaches. And the first was what is putting a pyrene PEG unit on it. So this is a synthesized compound in our laboratory, because we know pyrene ligands stick very nicely to graphene structures. And the length of the pyrene, which is in our case between 6 and 12, actually hinders really non-specific fooling. And this is what you see here actually. If you dip for 2 hours into a concentration of an E. coli of very high concentration, 10 to 8, you actually see that almost no bacteria stick to the surface. While in the second case, this is the assay images on the right, we had this pyrene ligand present, but now on the top, we put an antibody against the E. coli, in this case, an anti-Fimbria E. coli, and you see E. coli bacteria stick very nicely to the surface. So is this sticking to the surface now correlated to sensing? And yes, and this is what you see here. So we sense different E. coli concentration by using different pulse voltammetry on your interfaces, and you see the signal actually decreases with time because you have a deposit. You have a sort of linear range for different CU per milliliters, with a cutoff level estimated as a 95% of confidential limits of around 10 CFU per milliliters, and all this in 2 minutes. And you also see towards to the right ligand integrated to the surface, you're extremely selective to E. coli, because if you have SRAs around it, you would not get the same approach. So this was the first part, and I see time goes fast, and I already talked almost for 17 minutes. So quickly to the viral analysis. I don't think I have to go into PCR. If people didn't know it, by now everybody knows what the PCR is. But I quickly want to make a point that what an electrochemical sensor might be the most, well, has to be the most competitive with, is actually not PCR, it's a lateral flow assay. Lateral flow assays give you results in up to 5 minutes. Everybody can do them. But when you actually, and I simply take the example because we did this experiment, a lateral flow assay of COVID, then you can get a positive result only for CT values, which are 25. That means these are very rather low detection limits for viruses, which opted look for other methods. So you either amplify this kind of lateral flow assays, or you do like we decided to go for an electrochemical biosensor, which can also give you a quick result if you get the right ligand on it. So before I had talked about an antibody ligand for the E. coli. Here we opted for 2 different ligands. One was an aptamer. So you see this type of aptamer. We had worked together with BioPairs, an aptamer company actually in the States. And this type of aptamer has a nanomolar KD value for the S-spike protein of the SARS. And this is very interesting. So mostly of this aptamer is on the nanomolar range. So you can get this type of profiles from from LBA or SBI measurements. But actually, you can do now the same on a sensor. So what we did, we had a gold electrode. We did our surface chemistries to get it pegulated. And then mostly we played around with malimite tile chemistry to stick these aptamers on it. So you can see again with different pulse voltammetry, you can record the presence and non-presence of the protein for itself, but you can actually titrate it off. And you see, we get very nice KD values in accordance what's done on the ligand beforehand. So we are now in a position of measuring these viruses at different ligands. We get to limit of detection, which are around 50 plaque formant units per milliliter. And now to compare it back to our LF, that that relates to a limit of detection actually of a CT value of 33. So we went from 25 up to 33, which is actually even more interesting for COVID because the infectivity cutoff value is actually 33. That means even PCR can amplify further. After 33, cells actually hardly get infected. And you can also get very nice selectivity on this. So why did I talk about these type of things? Because this is what I want to finish up. Aptamers are still rather large charged species, which often are not so easy to handle on electrical and electrochemical sensors. So one of the ligands which are highly adapted for this type of sensors are something which are engineered antibodies, nanobodies. Nano because they're very small, they're only around 4 nanometers in height. And you can see here immediately the difference in charge transfer on this type of electrodes. If you would put a classical EGG on it, you have a very decreased signal. If you put an FC unit on it, so that's the one completely on the left, you get an intermediate. But if you would go to very small nanobodies, you get a very nice current signal. And because of these nice current signals, yeah, you can go to sensing. So actually, I will split this because I moved in time. And I will simply show you how these nanobodies can now be used for grape vine leaf virus detection. So grape vine leaf virus detection is caused by this grapevine leaf virus, which is actually transmitted by a soil-borne pathogen. It provokes severe symptoms, like you see all the leaves get yellow. But the most important thing is not this aesthetic loss, but you have an extreme economic loss and actually a threat that you're not allowed to harvest your grapes in time, because once this virus is present, it can spread all over the field, and there's currently no treatment for this available. So we said this might be an interesting example of developing a point-of-care devices which farmers can do on the site. So yes, there are ELISAs available. What you see here for a good ELISA result, you need around 2 hours. And the limit of detection of this commercial ELISA results is around 0.8 nanograms or 800 picogram per milliliters. So what did we try to see, and this is a collaboration with my colleague Christoph Ritzenthaler in Strasbourg. He designed a nanobody receptor with a nanomolar key day value, which should interact specifically to these grapevine fine needle diseases. So for this, we developed now again an electrochemical sensing platform based on this monoamide chemistry between the surface and the ligand. And what's interesting is now this type of viruses, they are not pathogenic, so you can much easier play around with them. So we played around already with some AFM images. So you see actually if the ligand is not present, our interface is extremely anti-fouling. So you almost see no of this virus is present. And then in the presence of the ligand, this virus, which is actually really small, it's only around 30 nanometers, so it's not so easy actually to detect it. You find particles present on the interface. That means there is definitely the ligand between these particles and the surface. Now you can say the intensity is not extremely high. I do agree. We're still working on this. So we are trying to use different concepts to integrate the density on this. But I think what's most beautiful is you see here, so you use this type of electrodes, you put this nanobody in, you plug it into your juice you get from these green leaves, which you grind it. And then what we do enzymatic enhanced electrochemical sensing. So for this, we actually integrate with a second nanobody, which is carrying amino phenylphosphorylate enzyme. And if one knows a little bit chemistry around this, it's this substrate APP in the presence of this enzyme will actually form the OH product on it. And this follow-up you can follow by electrochemistry. So you see here, you have a very small signal at the beginning, which is towards to this APP. And then over time, if the enzyme is present, you accumulate in signal. That means this time it's a signal on sensor, which has certain advantages actually to discriminate from other species. And this is what actually the results which came fresh from the press in the last weeks. So we can follow this now with different pulse voltammetry, looking the increase of this enzymatic reaction this time. And what we were really lucky is the limit of detection we actually get. So we get down in 10 minutes to around 10 femtogram per milliliter. So I want to put this into perspective to the ELISA beforehand. So the best you have currently on the market is around 800 picogram per milliliter. That means we seem to have an extremely sensitive sensor here on the market, which hopefully will help to, at a very early stage of virus being present on this vineyard, can give you an indication, and then the farmer can take the action which is needed. So with this, I want to finish. As you can imagine, this type of research, a lot of people are involved. So I want to thank anybody in one way or the other being part of this project. But then I also want to thank all people who believed on us and gave us some projects. And thank you for your attention.